have to talk about is definitely going to be ISO. It's been around for a long time, the idea of ISO. It used to be called ASA in some aspects of photography. So that was like, I guess, the American Standards Association. And film basically had two ratings. There was the ASA rating, which wasn't really used much towards the end and completely kind of died out when we went digital. And now we're starting to look at a thing called ISO, and some people like to call it ISO. It's up to you, it doesn't really matter to me. But basically it's kind of like a bare minimum standard that people use. I think it's the International Organization of Standards, but it's still called ISO. They like to flip things around or something. It's like they're astronomers or something and like to flip things around like magnitudes and stuff. But basically what it's saying is like there needs to be a standard for people to follow. That way if somebody says this is an ISO of 100, they kind of have an idea that that's going to be an ISO of 100. And what ISO basically means is kind of like the base sensitivity of your camera. And there's a lot of things that go into what that actually means. Like when you look into the bare minimum details and everything like that. And even cameras, when you're looking at ISO between camera company and camera company, there's going to be slight differences in what you're going to be looking at. But you can kind of get an idea that if somebody says it's an ISO 100, it's going to look pretty similar to your camera when you set it at ISO 100, and your scene is, very similar. So it's basically like a standardization of sensitivity, assumption of sensitivity for your cameras. And so when you're talking about changing the ISO, that actually means something entirely different these days as it did back in the day with film. Back in the day with film, when you would change your sensitivity, it would be like a chemical reaction is taking place that's a little bit different. And so the light that falls on it is creating a chemical reaction that's different than a different type of, or a different ASA, ISO film. And so back then, if you wanted to change your ISO of film, you would actually have to go and buy a completely different roll of film that is more sensitive than your other one, and you would have to completely change that out, and then you would have to get that processed differently than your other one. So it's a little bit easier to deal with ISO these days, but it has a completely different meaning when it comes down to the actual physics that are involved. And so all these cameras have a base ISO. And some cameras have like an ISO of 50. Those are going to be like your kind of highest end cameras. Most cameras have an ISO of 100 as their base ISO. But that doesn't always mean it's the base ISO. Some cameras' base ISO is 200. Like 200 is the happy point between two other functions that take place in the camera. And so that happy point can be 200 for some or 100 for others, and the happy point is going to be the ratio of what's called gain and offset. And so if you want to talk about ISO in a really good way, you want to actually talk about your gain and offset, because that's actually what it really means. Your ISO is like a way of describing how those offsets are getting you to your things, offsets and gains. So when you talk about raising your ISO, there's a lot of things that go into what that means. So in order to explain this in an easy way, we're going to use a little thing that a lot of people have seen. And so this is one of those pin art things. And so if you push on the back, you can see that it kind of creates like this residual image of whatever you're pressing against the back. And so this was like kind of like an easy way for me to help explain what we're doing. And so to describe how I'm going to set this up, I'm going to focus in on this so we can see the pins. So each of the pins on here, we're going to say that those are pixels, okay? So each of these pins represents a pixel, and depending on how many pixels you have, basically tells you how much resolution you have per given area. And so the area of this relative to the size of the pixels is pretty bad. You probably don't want a camera with this ratio, because if you basically kind of look at my finger, you just basically see the shape of the finger but no details in there. So if you wanted to get details of my finger that are, let's see, if you want to get details that are finer, like on my finger, like all the little ribs or whatever you want to call those on there, you would actually have to make the pixel sizes smaller than the size of like the details that you want to see. So that's not a very good thing, not a very good pixel resolution on here. So that's what we're going to use. And then the height here is going to be what's called your well depth. So your well depth is basically going to be how much light your pixel can take before it's oversaturated. And so by raising this up, let's say we have 50,000 photons of light that can hit each of these pixels before it becomes saturated and it hits the top right here. So that the top right here is going to be our limit for saturation. Hope that makes sense. And so there's also an idea here about your bit depth. So if we wanted to read each of those pixels out, if we had a bit depth of 1, basically anytime that a pixel would detect a photon, it would automatically go up to its highest, or it would always read off that well depth as 1 photon. So anytime these fill up with anything, no matter what, it's going to read off one electron that's converted from a photon. So that's your pixel depth right there. But if you wanted a higher bit depth, basically you would read out different gradations. So like, let's say each of these pixels had like a level indicator on here. And higher bit depths would mean there's more level indicators from here. So instead of being 1, from 0 to 1, it would have like 2 bit depths would be 1 to there, 4, you would have 4, and then 16 would be 16 gradations upon there. That way, if it reads out, it'll read out each one of these steps instead of just one thing there. So that means it basically means that you have more dynamic range, because you're able to tell differences between bright sections and dim sections with more levels. So that's kind of where that idea comes from. So when you're talking about other things like background noise, if there was 0 noise on the sensor, every single one of these pixels on here would actually read off as 0. If there was 0 noise on here, all of these would be 0. But inherently, all sensors have kind of a background source, and it could be from thermal noise or some other noise. And so all of these are going to read some kind of background level of noise. So that's going to be your bias as you would learn it in astronomy. But it's also something that you can think about in kind of anything that has a digital recording device. Even in audio, there's always a bias. That's your background noise level. And so that basically means that all of these are not 0. They're all at least 1 or 100 or 1,000, depending on how bad your image sensor actually is. All right, so if we have an object, let's say it's a universe, and so this is our sensor here. We're going to put the universe back here. So if we have a really low signal, only going to show up this much between the background. And so if we have a lot of background noise, what can start happening is the background noise can start overtaking the signal, and so this kind of goes kind of completely white. We're overexposing it, and we don't have a lot of detail in the stuff around it. And we can see that our noise down here is pretty high in the background. So what we can do is, with a better sensor, we'll kind of trick this. With a better sensor, we can reduce the background noise, and the signal that we introduce is actually going to be a lot higher relative to the background noise. And so that'll give us a brighter overall image without having it overexpose the image or the signal itself. And so we can get that there, and then you'll notice that we're not overexposed, but we have really low background noise. And so that's kind of what we want to, that would be an ideal camera if we were to do that. So when we're talking about raising the ISO, basically what we're doing is we're setting kind of the background levels a little bit higher. We're compressing the background levels. We're compressing the background levels into the signal levels. And so basically what happens is everything starts getting raised equally. And so if we go back to what we were doing before, raising the ISO also raises the background noise at the same time. So the noise that's already there, it's not actually making the chip more sensitive. You're just removing some of the dynamic range by getting rid of some of the gradations here, and then you're compressing the signal into the noise a little bit, and that's why it always, like higher ISO always appears like it's a lot more noisy, is because you're kind of pushing those down together. And so if we do it too much, it won't allow us to do too much on this for some reason, but if we keep going too far, what will happen is your image will be overexposed. You'll have a lot of background light and very little detail in there, and that's actually what happens in real life when you take a picture with really high ISO. Your signal gets really bright, your background gets really bright, and you don't have much detail, and you can't tell much of a difference between them sometimes. So it's not always a good thing to have super high ISO, and so that kind of gives you an idea of how that works. And coming back to the idea of what I was talking about with offset, sometimes what happens is the low noise right here will, when it reads out from the camera, it won't be very different from the signal, and so you can actually get a very low signal because things aren't offset properly, and so you'll have a very low signal relative to the background. But adding an offset in there can help pull a little bit of that signal out, because you offset the read, the overall signal from the entire chip, so you can kind of distinguish between the signal and the noise a little bit more. So I just want to kind of give you an idea once again that ISO doesn't actually make your chip more sensitive. There's always kind of going to be a bare minimum sensitive. What some chips and what some astronomy cameras do, though, is what they'll do is they'll kind of add together several pixels and read off those several pixels all as one pixel. And so basically your image, or each of your pixels that you're reading off, is going to be 4 times more sensitive than any single pixel. So overall, when you download your image, it's going to be smaller. So that means like this 8x10 image would be maybe like a 6x5 or 6x4 or whatever. So your image is going to be smaller, but each of those pixels that you have in this new image is going to be relatively brighter than any single image or any single pixel on your normal non-binned, that's what it's called, binned or binning, non-binned image. And so that's one way to do it, and some camera companies are starting to do that more and more. They kind of stole a little bit more from astronomy and started binning the pixels and stuff like that. That way they can increase the relative sensitivity that you're getting from your camera. But like I said, you get overall a smaller image by a quarter every time you bin them like that. And so coming back to the whole thing about resolution, is if you don't have a lot of resolution, you're not going to be able to tell the fine details in your object. So if we were to switch from this relatively non-detailed image of our university's U to something that's a little bit more like this, where there's a lot more fine detail, since our imaging sensor doesn't have a lot, or doesn't have small pixels, we're not going to get very much detail out of there. And so we're actually missing detail on several parts, but you can kind of get the overall general picture that we're looking for. It's just not very detailed. And so if you wanted to get a much finer image of this, you would get smaller pixels, or zoom in with a type of lens, or get a bigger object. You can do any one of those three things. And then if you do a lens, it's going to zoom in on your image better, and then that image that you're trying to obtain is over a larger number of pixels. So each of your spots on your little image will have spread out a much larger area. So that's one way to get around that. Okay, so now that we've talked about all those things, like what happens when you do a long exposure. So long exposures are good things and bad things. So with long exposures, you basically are keeping your image sensor open to light for a longer period of time, which means each of the pixels that you're getting, so basically like each of the pixels that are on here has more time to gather light from your image or from your object. And so you'll start off something similar to this, and the more time you put into it, the brighter the signal is going to slowly come out of the background, and your image is going to get better and better. But as you're doing that, all of the noise that is inherent on your chip starts to come out more too. And so you got two things going on. You're getting more signal, but you're also getting more background noise. And so you don't want to leave this open for too long, because eventually you'll reach saturation on here, and then you'll basically lose all your detail there. So you have to find the right ratio from your signal to where it doesn't want to start oversaturating. So that's something you have to worry about there. So what you can do, especially in astronomy, is take a bunch of images where you have some signal, but it's not getting to your saturation point, and it's keeping the noise low. And then you stack multiples of these images over and over and over and over, and you start building up that signal out of your background. And every time you add a certain number of images onto your stack, your background is decreased, your noise is decreased, and your signal is increased. So that's one way astronomers have figured out to get a better an overall image of that kind of stuff. So that's something you can do even like with regular photography. Some cameras are trying to do that now, where they're taking multiple images of a scene, adding them together, increasing the overall signal, but also increasing the overall megapixel count, and adding them all together in camera and spitting out a much larger megapixel image with a higher detail and better contrast and all that stuff. So they're slowly catching on to what astronomers have been doing for many years already. And so this is also something that's kind of it's moved from chemical photography or film photography into digital photography, because there were some people that were doing stacking of like a few frames of film a long time ago too. So it's not something totally new, it's just new for this kind of thing. One thing that it does also, though, if you're taking long images of stuff, you're using something that is using electricity, and that electricity is charging up all of the pixels. That way they can start taking in photons and converting them to electrons. And so as you're using that electricity, you're kind of heating up the chip itself and the electronics around it. And so if you're using a DSLR or a mirrorless camera, your electronics are heating up more and more, and that actually raises some bits of noise in the background. And the longer your exposures are, the more this bit of noise starts to increase relative to your signal. And so if your camera is too hot, you're actually going to start getting so much noise in the background that your signal is not going to make much sense to keep going. So some astro cameras that are out there today actually have a thermoelectric cooler that's attached to the back of the electronics, and it helps to keep the entire chip cold. That way you're not getting all of this excess noise due to heat from the camera itself. And so those kind of cameras cost maybe a couple hundred more than a similar non-cooled camera. But if you're doing something in astrophotography, and you can afford that little bit of a difference, it's actually good to get that kind of stuff because you'll have much nicer images overall for a longer time. There's something also called a dark frame, and in regular cameras, basically they call it long exposure noise reduction or some form of that. And what they're doing is they're taking a picture of that heat noise, the noise that we were talking about with that. And so you'll get a repeated signal of noise from heat over your chip. It changes a little bit over time, over the course of years, but this signal that you get, this background signal that you get, can be kind of removed. So what you'll do is you'll take an image of just this background noise due to the electronics heating up and stuff, and from the digital noise of downloading and converting and everything else like that. You take an image of all this stuff, and then you stack several of these to get rid of like any extraneous bits of data that come in there, maybe from like a cosmic ray or something like that. You stack those, and then you can subtract this from your image itself, and then all of the noise that's inherent with that that heat noise and stuff kind of goes away. But there's a couple things that you have to be aware of. First, you have to match your ISO. Second, you have to match the time, and it's actually best to match the temperature of the sensor. And that's really hard to do with a digital camera like a DSLR or something, because if you're taking images when it's like 20 degrees outside and your internal temperature of your camera is reaching like 40 degrees, that means you have to try to match that same temperature in all those situations when you're at home. So if you're doing DSLR stuff in the field and it's cold and you can't take care of it later, just take the dark frame with each of the images, and you can set your camera to do that, and it'll subtract it out of all those, and you'll get a much nicer image overall. If you have like one of these cooled astro cameras, you can keep that sensor at the same temperature all of the time, and so you can do this stuff. You can take those what are called dark frames at home later on. That's basically what you're doing. A dark frame is just an image of all the background noise due to time and temperature on your chip. And so this is pretty repeatable, and you can build up what is called a library of these things, and you can take care of those later on whenever you want. So another thing you need to be aware of is that the file types that you're taking all of this in is really important. I always shoot, and most photographers just always shoot in RAW because it's an uncompressed file format. And so basically whenever you're shooting in RAW, you're just reading the chip off and you can do whatever you want with it later. If you convert that to an in-camera JPEG, it is actually compressing all of that data down to a smaller file, and it's actually throwing out and throwing away a bunch of data. And so if you're doing astronomy photography, or really any photography, you don't want to throw away all that extra data, because like on my shirt right here, it's a little bit black, but if it was a JPEG, you would lose any of the detail that you could detect on the shirt or the images behind me, and you won't be able to adjust for like if this spot over here is too bright, you can kind of get rid of a little bit of that. It'll help you with sharpening and stuff. It'll help you with noise reduction and stuff later on the computer. But if you do it with JPEG, all of that's kind of taken care of for you, and it's much harder to adjust the blacks, adjust the whites and everything else with that, and also much harder to stack them together later on if you're doing stacking astrophotography images. So basically that's kind of all. There's a couple more things we can talk about with photography, and that's just composition. It actually moves from composition of regular photography, like the 2/3 rule. Some people like to compose with your body over on the left or the right, with more room above you or more room below you, depending on what's going on. You can do that same thing with astronomy pictures. If you're taking a picture of a nebula, you don't always have to stick it in the middle. You can stick it off one side or another to give you a little bit of that kind of perception of depth in space. You just think about that kind of stuff when you're actually getting your images, and you might actually come up with an overall better image just by composing it slightly different. Not everything needs to be in the center. Something that is taught in photography classes for the last 100 years is don't always put somebody's face right in the middle of your image, because it can actually make some people who are viewing the image a little bit uncomfortable. It's a weird psychological aspect of photography that you can actually make people uncomfortable depending on how you have images set up and stuff just on pictures. So try to bring that into your astrophotography also, and kind of think about how things are best composed for your stuff. And then when you're talking about all of this stuff, when you're talking about the cameras, different types of cameras and stuff like that, different types of lenses, there's always going to be a slight different view of the sky depending on the lens and the camera and all that kind of stuff. And it comes from wide angles can cause this kind of aspect to it. Like in this picture right here, you get a wide angle with the whole Milky Way going across. You lose detail on any of the individual aspects. You zoom into something like these ones right here, and you gain all of that extra detail, but you lose, like this is part of the Orion Nebula, you lose the rest of the nebula that would be over here. And so you only get this little small aspect of the nebula or a galaxy or this nebula over here, but there could be so much more that you're wanting to see with that. And so you need to choose your camera and your telescopes, and even your astro cameras and stuff based on the type of objects that you want to use. Some people have multiple telescopes and multiple cameras, and so if they want to do a wide angle view of, let's say, the Orion Nebula, they can be zoomed out and get the entire nebula and stuff in there. Or you can use a bigger telescope, a wider or like a 14-inch or a 10-inch, and you can zoom in on galaxies and stuff a little bit better. So it just depends. You want to plan that kind of stuff before you purchase. Like, where do you want to start? Where do you want to go? And what you want to do it with. The thing with using DSLRs is all of the stuff that you need is kind of held within the camera itself. You have the battery, you have the processing, you have the downloading, you have the saving, you have the control, all in just one little case. If you get an astro camera, you have to bring a laptop or some kind of controlling device with you to be able to control all of that stuff all at once, because it doesn't have any of those types of things built into it. And if you're doing long exposure astrophotography with either of these, you want to take into account that your telescope is moving, your mount is moving. You need to be able to control the mount. If you have an astro camera and you're bringing a laptop, you may as well get like a guiding camera and stuff with it, so you can do longer exposures. That allows you to decrease your ISO, so you're not getting like those compressed levels of signal and noise in the background. And it actually helps to bring out a little bit finer detail, doing more exposures with lower ISO than doing fewer exposures with higher ISO. It cleans up your image and everything also, but with those longer exposures you need to do longer tracking, and so you have to have a tracking telescope on your mount. That way your mount is precisely guided across the sky as the sky is moving, and helps to get rid of any of the bumps and stuff from the drives. So there's a lot of little aspects that we're going to actually talk about later on in future videos, and there's a lot of other videos out there talking about aspects here and there of this stuff, but hopefully I can bring it all together in one series. It might take a while because there's a lot of stuff. You'd be surprised at how much stuff goes into this, and you guys have just watched a long video about just photography, and this is kind of scratching the surface of photography. This gets you, you can jump into any of the points that we've been going over here and go into a rabbit hole for a long time on any of those aspects of this stuff. And so and that's what I would encourage, is looking into each of these aspects a little bit more so you can understand it a little bit better, and so you can become more aware. And with that awareness and those understandings, you actually get to expand your knowledge and your abilities to take all of this stuff and throw it together and bring it all in together, and you'll get better images and stuff overall and have a better experience later on, and you can have a lot more fun with this. So hopefully this helps everyone, especially those getting started with photography and hoping to jump into astrophotography. Hopefully it gives you a couple ideas of where to go and what to understand when you're looking at these different aspects. And just like any of the other videos, feel free to ask questions on any of the equipment that we have, or any of the ideas that have been promoted here. So it's kind of a free idea place, so feel free to ask. Thanks for watching. Hopefully it wasn't too long, and hopefully it wasn't boring. So I'm going to try making things a little bit more pepped up and stuff than our older videos. So hopefully it keeps your interest and lets you be a little bit, you can follow this stuff a little bit easier. So everybody have a good photography and astrophotography session next time you get out there. Thanks, and bye-bye.